Everyone, thanks for watching. I thought I would talk out the selective discharge problems you saw in your mock exams. As a quick reminder, selective discharge is relevant in electrolytic cells. In an electrolytic cell, we have some electrolyte and we have a cathode and an anode, positive anode, negative cathode. The electrolyte can be either aqueous or molten. In the molten situation, it's relatively straightforward. I can have any ionic salt, let's say ClCl2, for example. In molten or aqueous situations, we're going to break up into our ions. And then if I'm in molten, well, easy enough. Each ion goes to the appropriate electrode, positive to negative electrode, negative ion to positive electrode. I write out the reduction of calcium, the oxidation of chlorine, and that's the reaction that's going to happen. I'd get some chlorine gas being evolved here from the oxidation of chlorine, and I'd get some solid calcium being produced and deposited on the cathode from the reduction of Ca2+. All right, easy peasy. Selective discharge comes into play when I add in water, when I have an aqueous situation. So for example, if I had NaOH aqueous, well, I have the ions from NaOH that could reduce and oxidize. I also have water that could reduce and oxidize. So I have to decide which is going to be better. The rule that I'm looking for is the more negative my E naught value or my cell voltage value, the more likely to oxidize. A standard electrode potential, sorry, was the word I was looking for there. Okay, this rule is true when I'm looking at a reduction reaction. So, easy enough at the cathode, I'm looking at two reduction reactions. I have the reduction of Na+, the reduction of water. More negative, more likely to oxidize. More positive, more likely to reduce. Well, H2O is more positive, so H2O is preferentially reduced. This is the reaction that would actually happen at the cathode. At the anode, I have these two options, but notice these are, of course, written as oxidation because I'm at the anode. And so my rule, well, actually the opposite would apply when I have an oxidation reaction. So the more positive the standard electrode potential, the more likely to oxidize when I'm looking at an oxidation reaction like I am here. So this reaction with OH minus is more positive, less negative, more positive, same thing. And so this is the thing that actually happens. These are the products that I would make. All right, so you had two examples of this in your mock exam. The first one was looking at dilute aqueous copper 2 nitrate electrolyzed using platinum electrodes. We talked about a couple situations when we talked about selective discharge. We talked about the effect of concentration. We also talked about the effect of the type of electrode. Now, I think this was kind of unintentionally, or maybe intentionally on the IB's part, I don't know, obscure. This was one of those problems that some teachers complained about, but such is life, I guess. So dilute copper 2 nitrate. I think some of us got caught up in dilute and said, hey, it's dilute, so it's just water that we're going to have to deal with. But really the key here was looking at knowing what happens when we have inert electrodes. This was actually one of the examples that we walked through in class. The one in class was with copper sulfate, not copper nitrate, but same idea. So when I have an inert electrode, the thing that's going to happen is, well, at the anode, when I have an inert electrode, water is going to be preferred. You'll notice, and we talked about this in class, they didn't even show us, in this case it was sulfate, in our case it was nitrate, they didn't even show us sulfate or nitrate trying to be oxidized, they just showed us water. This is an oxidation reaction, so looking at this value, it's pretty negative. they didn't even bother comparing it to another one. And we talked about inert electrode, we're looking for water to be oxidized. Now, I didn't love this question because, of course, you don't have the data booklet to think about the cathode. Some teachers recommend that you're at least familiar with the electrode potentials. I don't think memorizing section 24 of the data booklet is a great use of your time, but this is a particular reaction that shows up in the textbook that they like to ask about. So it might be a good idea at least to have a sense of which ions are further apart from each other in the standard electrode potential book. So, or data section 24. So copper and water are pretty far away from each other. You notice these are pretty different, and copper is way more positive here, so it's more likely to be reduced at the cathode. So at the cathode, we would get copper from Cu2+, and they actually did give us this value, and we would get water at the anode. We have platinum, an inert electrode. They gave us copper, and so maybe being familiar with just the water values would probably be worth your time. So if I know that water is about -1.2, -0.8 for the oxidation and reduction respectively, that would help with answering questions like these. I know it's a lot that they're asking from you here, but this was one that we saw in class. So feel free to ask me any follow-up questions you have about that one. Here was the other one that we were looking at, and this was with the ammonium nitrate. And here, again, they gave us some E0 values. So we're going to specifically use the data that they give us. All right, I have ammonium nitrate. It's going to break up into its ions, and it's aqueous, so I have to decide, are these reactions going to be preferred or water reactions going to be preferred, just like I saw here. All right, let's start with the anode. Sure. Anode is positive, so the negative thing goes to the anode. And at the anode, I'm going to do oxidation. Okay, I took a look at the information they gave me. I notice I don't have any values for the oxidation of NO3 minus. I have reduction of NO3 minus, but when I reverse this reaction, well, that's oxidation of NO gas, not NO3 minus. So I don't know anything about NO3 minus oxidation, and I'm only supposed to use the values that they're giving me. So NO3 minus can't be oxidized there. I don't know what its standard electrode potential would be. So the only option that I would have would be water. Water could be oxidized. I definitely have water in there, and this reaction can just go in reverse to oxidize water. So I can get here H2O yielding 1/2 O2 plus 2H plus 2 electrons. These reactions, of course, are reactions that you should know, the reduction and oxidation of water. Notice this is indeed the oxidation of water that you've already memorized. They just are giving it in the simplest ratios, and here they're giving it to match the equation that we had. All right, so a little tricky, but really I was just making sure I'm using exactly the information given. I don't know anything about NO3, so the only, out of the reactions they've given me, the only one that could have been oxidized was this water business. All right, so now at the cathode, well, at the cathode, who would go to the cathode? Cathodes are negative in electrolytic cells, so my positive thing is going to go to the cathode. Great. And so I would have the reduction of H2O or the reduction of NH4+. Now, reduction of H2O, I don't have that information, so I can't even consider. They did not give me the reduction of H2O. We just saw on paper 1, maybe they want you to have it memorized, but I'm only supposed to be using the given values, so I'm not going to go to the back of my head, remember what the reduction of H2O is, remember the E0 value. It's not given, so I can't consider it. So all I can look at is the reduction of NH4 plus. Well, NH4 plus, let's think about how that would exist in solution. It would exist in equilibrium with H plus and NH3. So they don't bother giving me NH4 plus, but they do bother giving me information about H plus, which is also going to be there in solution. Because I have NH4 plus, it's aqueous, it's going to break up. And so H plus the electron yielding 1/2 H2. Well, out of these three equations that they gave me, this is the only reaction that could be happening at the cathode. So that leads me to the anode. I have the oxidation of water. I didn't have any NO3 to compare it to. And the cathode, I have the reduction of H plus, and that H plus came from the NH4, which was attracted to the cathode because that was my positive ion. The cathode was negative. So this one is super easy to overthink. I definitely overthought it the first time I did it, but now we know. All right, thanks for watching. Let me know what questions you have. Bye.